Okay, because there are quite a lot of you, I need to be able to have a question and answer session, which helps me understand what you do and what you do not understand. Okay, that's really important. So we use this and that, and sometimes this. So what I'm going to do in a moment, I'm going to be asking you how well you understand some words which are used, some terms which are used to do with energy.
See,
And Shirika, I'll have to mute you, sorry. So what I'm going to do is I'm going to show you the topics that we are going to be dealing with. And I will be asking you whether you have heard of them, yes, no, and just maybe. I will also be asking you sometimes whether you understood what we have done, because there is no point in me teaching you material which you already know very well, okay? Some of your teachers will be very, very good at explaining particular topics, and then I would be wasting your time if I did them all again. But so what I'm going to do is sometimes I will say, okay, can you tell me whether you understand that? And it's got to be yes, no, or maybe. And I need all of you to be involved, not just the people in the front. Okay, so here we go. I'm going to share a screen. The screen I'm going to share is this one. If it will share, which is good. So come on, slideshow. Okay. So we're going to be talking about energy. And we're going to be talking about the sort of energy which you see every day. We're going to be talking about things like fire. Today, we're going to start by talking a little bit about cooking, but I'm going to also talk to you about, I'm going to be asking you about what you understand already about energy and what we call heat energy or enthalpy. So what this topic covers is, firstly, endothermic and exothermic changes. I will be asking you whether you already know about those. We will be looking at energy level diagrams. If necessary, I will show you one before you tell me whether you know about them. We're going to talk about Hess's law, which is for some people a little confusing, but it doesn't have to be. Chemistry is actually a pretty simple subject. We're also doing bond energies or bond enthalpies. We will be looking at latent heat, which is only physical changes. And we will finish by looking at how we measure and calculate enthalpies or heat energies practically, which is in November, you will do a paper 3, an examination 3, which is the practical one, and I will help you know exactly what you need to do. But before we go any further, I'm going to ask you whether you feel confident about these: endothermic, exothermic, energy level diagrams, bond enthalpies or energies, latent heat, which you may not have come across, measuring, and Hess's law. Okay. So I'm going to stop sharing now, and I'm going to come back to you. And I need to see thumbs. It's very important that everybody shows us what they know and what they don't know. So the first question is, how many of you are confident, not confident, about endothermic and exothermic changes? If you've never heard about it, it doesn't matter. But confident, endothermic and exothermic changes. Come on, guys. Mathari, mixed secondary, I want to see your hands. It doesn't matter if you don't know. So if you don't know, it's like this. If you do know, it's like this. Genesis, well done. Well done, Genesis. Very good. Silver Spring, let's see. What do you know? Do you know or not? Don't look at the teacher. Look at me. Come on. Okay. Mathari, can I see again, please? Mathari, mixed secondary. Okay, cool. Okay. And Wamwini, I can't see you. Dandora, I can't see you. Silver Spring, I can't see the individual students at the moment. See if you can get it so I can see them, because it would be very useful. Okay, the second thing I need to ask you about is, how do you feel about energy level diagrams? I'll show you one first. Okay, I'm going to show you one because I don't want to teach you stuff which you already know. So I'm going to change to my other camera. And here, an energy level diagram can look something like this. I haven't labeled it, but I hope you can just about see that. I know it's a little bit of a long way away, but there it is. Okay, that's an energy level diagram. It's energy up the side and sort of like time along the bottom, though it's not actually that. I'll come back to my other camera. So can you tell me, have you seen those before? Do you know what they're about, or do you not know what they are about? Mathari, mixed secondary. Yes? No? No? Okay. Silver Spring, thank you very much. Wamuini? Maybe, but not entirely. That's good. Genesis, thank you. That's brilliant. Okay. I'm not sure which school I'm looking at with you, Mr. Adoli. You're muted.
Horizon Secondary, New Horizon Secondary School. It's a new school.
Excellent. Well, welcome to you and your students. Thank you very much for being here.
Good.
So, New Horizon, do you understand profiles or not understand profile? Or have you seen, not seen? Do you know them? You mustn't be ashamed. You mustn't be ashamed if your teacher's there and you still go, I still don't understand it, because sometimes I teach a lesson and people go, I don't know what you're talking about. And afterwards I go, do you understand it? And they say, yes. And then they don't. So even if your teacher is there, classes, and they're looking at you and they're going, yes, we've done that, you must be honest and you must say, no, actually, we didn't understand it. Okay. All right. The next is bond energies. Have we done bond energies or not? Genesis, Wamuini, Mathari, Silver Spring, bond energies, yes, no. Have we done? Do we not understand? Thank you, Mathari. Thank you, Genesis. Some of you in Silver Spring, okay. Wamuini, bond energies. Okay, that's fine. Good. I think I'm not going to ask you about latent heat and measuring and calculating because we need to start further back. That's fine. Okay, so the basis of this is we're going to talk about cooking to start with. And I want you to just imagine that we're going to cook some ugali or something like that. And you have a stove, and the stove is burning something. Let's say we're burning some wood, and we're burning wood, and heat is coming out of the wood. Now, this is, when you think about it, it's a little surprising because all that energy comes out of the wood. Where was that energy in the wood? That is what we call an exothermic reaction. Exothermic. I'll write it on the board in a minute, but I'll show you a slide about it. But what's happening inside the cooking pot is something where the food is cooking and it is absorbing the heat and it changes the food inside. That those sort of reactions where energy is taken in is called endothermic. So what we're going to do is we're going to look at a couple of pictures which might help you understand that idea. So, okay, so here we are. So here are two pictures which you can't see at the moment. This is an exothermic reaction. That word, exothermic, thermic is something to do with heat, therm, thermometer, and so on, something to do with heat, and exo is like exit, the way out. So an exothermic reaction gives out heat. If you write just one thing down, just write down exothermic is a reaction or a change which gives out heat. The opposite is endothermic. Endothermic means heat is taken in. So in my example of cooking the ugali, the stove, the reaction in the stove is the wood burning, that is exothermic. Whereas what is in the cooking pot, the changes which are happening in there are endothermic. So the food needs to take in heat to change into the finished product. And the wood burns down and becomes ash. And in doing so, it gives out heat, exothermic. Okay, so exothermic for the fuel and endothermic for the process. Okay. Okay. So here are some things to do with exothermic and endothermic, and these are basic ideas. So the stove gives out heat. It's actually the wood which is giving out the heat, and we will work out how it is that it gives out heat. We will also talk about endothermic, where heat is taken in, and that's very important. Now, this is something which is a little bit more difficult to think about. And I'm going to come back to this in just a moment with a little demonstration. So products are more stable than reactants. I need you to know the words reactant and product, and I will show you them in just a minute. For endothermic reactions, the products are less stable or higher energy than the reactants. So I'm going to show you what I'm talking about there. I'm going to stop sharing just for a minute. Okay, so if I hold a pen up in the air, is it higher energy than it is later if I drop it? Is it higher energy or lower energy up here? Higher, lower. Okay, when I hold it up here, I'm going to drop it. I drop it. Okay, is it higher or lower energy up here? Who thinks higher and who thinks it's lower up here? Come on, be brave. Let's see your hands. Students, come on, you need to interact. So Genesis think it's lower. Dandora girls think it's higher. Silver Spring are keeping their thumbs to themselves. Mathari mixed. I saw a hand at the back. Good, well done. Good, correct, courageous, good. Usharika, higher or lower up here? They think it's higher. Now, the question is how we know whether it is higher or lower. So I'm going to drop it again. Listen. That sound which comes out tells me that it was higher energy up here. Why does it go down? Ah, well, gravity and so on. And if you do physics, they will talk about potential energy changing into kinetic energy, which is movement. As the pen drops, it loses energy. And that energy I know is given out because I can hear it. So in chemistry, we also think higher in energy are higher up. And if something goes from a higher energy to a lower energy, it gives out that energy. Okay, so exothermic reactions, where we start, and the word is reactants, where we start is higher than we end up. So we end up lower down and that energy is lost. And we will see that in a picture in just a minute. But I want you to look first to get an idea of what an endothermic reaction and an exothermic reaction could look like. They're very quick. So I'm going to share. Okay, I'm going to go for an exothermic one first. A nice picture of a lion, nice friendly lion. Here's a very quick exothermic reaction. I hope, as long as it loads okay. It's very quick. So this is a fire. So what is happening here is that we start with a little pot, and it has just started to burn. But as it burns more and more, it gives off a lot of heat. That is exothermic. And afterwards, there is actually some molten iron in the bottom. This is how they mend railway tracks and so on. They get a mixture and they set fire to it, and it melts iron down to the bottom. This melted the pot completely. That is a lot of heat. Okay, so that one there, that's an exothermic reaction. So let's go back and let's have a look at an endothermic one. This is a chemistry teacher doing a little experiment. It's somebody I know. It's a little experiment, hopefully. So she's got two solids. It doesn't matter what the solids are. What I want you to do is I want you to watch when these are mixed together, what happens when she puts the thermometer inside it, okay? She has a little amount of water on this watch glass, and she's going to put the beaker on top of it, and the endothermic reaction will do something to it. I might turn her voice off so I can tell you what's happening. So she puts down the first powder and she adds the second one to it, but she shows the temperature at first. And the temperature says that the temperature is not very high. It's 16 degrees Celsius. Now she adds the chemicals. She missed with some of it missed. Okay, she adds the two together and they start to change. They start to become more like sticky to each other, and they become more like a liquid eventually, and eventually they become a real liquid. But look what happens to the temperature according to the thermometer. So she's mixing that. Wow, that's gone down 20 something degrees. That is much, much colder already. So it's now become much more like a liquid. Let's see what temperature it has gone down to. That shows it is producing ammonia, and it's at minus 21 degrees Celsius. That's very cold indeed. If you kept your fingers in that, they would freeze. You would get frostbite. If you went to the top of Mount Kenya, it does not get that cold at the top of Mount Kenya. And this picture here is showing that this beaker is so cold that it has frozen the water. So now the ice holds the beaker to the watch glass. Okay, so that's what's happening. Okay, so I'm going to stop sharing just for a minute. So exothermic reactions are often quite violent. They give out a lot of energy. The energy sometimes throws the chemicals around, and they are hot. They get seriously, seriously hot. Endothermic, they get much, much colder. Much colder. And that's very important to understand that the endothermic ones are absorbing the heat from the room and so on. And the thermometer, which she stirred the chemicals with, that was saying it went down to minus actually 27 eventually. And that's because all the heat was being sucked away from the thermometer, and the thermometer was saying this is minus 27. The exothermic one actually gets to 1600 degrees, 1600 degrees. That's enough to melt iron, which is what was happening. Now, what I want to do is to show you that on my other board. So I'm going to change here to my other camera. Okay. So hope you can, I know that's a little, let me just turn down the lights a little bit, see if it's easier to see. It's not great, is it? I'll draw it bigger and hopefully it will become more obvious. Okay. So if I have energy up the side here, up the y-axis is energy, along the bottom is progress of reaction. That is different from time. It's different from time because time definitely goes in one direction. Progress of reaction tells me that I could go this way, but I could go this way. So in the first example, the exothermic reaction, if we're talking about wood burning, if we're talking about the thermite reaction, which I showed you on the screen, we start at a particular level. And we call the beginning chemicals reactants. I hope you can see that, mostly. Okay, reactants. A certain amount of energy has to go in. Like if we light a stove, it doesn't just catch fire. We need to use a match or a lighter to give it a little bit of energy. So it goes up in energy to start with. And then it gives out energy. And it does that because the things which are produced are lower energy. And they are called products. So, yeah, I can just about see that. So reactants turn into products. Wood into ash. The thermite reaction, the chemicals are iron oxide and aluminium, and they turn into aluminium oxide and iron. A candle. I don't know if you know, but in a candle burning, it's the wax that burns, not the string, not the wick. So here's the wax, here's carbon dioxide and water, which are the only two things which are produced. But the important thing to know is that it has to go up first. It needs to go up first. And up at the top are what we call intermediates. Intermediates are the chemicals which are sometimes formed on the way through a reaction. So we start here, go up to there, drop down the other side. And the amount of energy which is given out, just like dropping the pen, is the difference between these two levels. So from here down to that level. That is the energy that is given out. Okay, that's the energy which is given out. The difference between here and there. Because the bit that we go up to here, we get back, going back down to just here. So that level is like 0. That level all the way across is 0. So the energy given out is from here down to there. From here down to there, the energy is given out. An endothermic reaction looks different from this. It's the other way up, really. It starts lower and ends up higher, and therefore that amount of energy has to be taken in. And I'll show you the picture in just a minute. What this amount of energy given out is called delta H, and it is shown like this. And we're just going to look at a slide about that. So I'm going to change back to my other camera. Sometimes I will be able to do a lesson from a laboratory, but today I can't access a laboratory, but I will try to sometimes. And I'm going to be producing a lot of little experiments which I can show your teachers, which they can then show you as well, which is cool. Okay, going back to this. Okay, so changes in, and the word we use is enthalpy. Enthalpy is a word meaning heat energy. So if you didn't know that already, it would be worth writing down enthalpy equals heat energy. You will know many types of energy. You will know electrical energy, chemical energy, movement energy, and so on. But in chemistry, most of the time we talk about heat energy because it is easy to measure with a thermometer and so on. And most reactions give out or take in heat energy. So this is enthalpy. So changes in enthalpy are called delta H, and it means change. So the triangle is actually a Greek letter D, and it means change in something. So if we had a change in temperature, we could put delta T. If we had change in anything, we can put this triangle before it. H stands for heat energy or enthalpy. And so we use the term delta H. That's what we say. We say delta H. So let's have a look at how we use it. So delta H means change in enthalpy. There it is. So if we've got an exothermic reaction, heat is lost. It's given out. It's given out of the wood to the cooking pot, or given out in the thermite reaction to melt the iron. So delta H is negative. So the number, because we are going to have a value for this, is negative. If it's endothermic, heat is put in, and so the delta H is positive. Let's see a couple of examples. Oh, sorry, here's some examples. Examples which are worth knowing. The most obvious exothermic one is burning. The most obvious endothermic one is melting. If I get an ice cube and I leave it to melt, if I keep it in the freezer, it will not melt. So I need to heat it up. I need to add heat to it to get it to melt. Usharika School, your teacher Godfrey will not be very impressed with you. Yeah, your teacher Godfrey will not be very impressed with your behavior at the moment. If you cannot learn anything from me, that's fine, but I don't expect to have to talk to you like this. Another kind of exothermic reaction is neutralization. Neutralization with an acid and an alkali, that is always exothermic. Another endothermic one, it's a change, not a reaction, is boiling. Another exothermic is some things dissolving in water give out heat, some things dissolving in water take in heat. So if I got some water, 2 cups of water, and I added NaOH, that's sodium hydroxide, to one of them, and KNO3, which is potassium nitrate, to another one, and I stirred them, the NaOH thermometer would show it was getting hotter, and the KNO3 one would show it was getting colder, but they're both dissolving in water. Magnesium, when it displaces copper, is a very violent reaction, and it is exothermic. Photosynthesis, what green plants do, is very much endothermic. It takes in a huge amount of light, but also heat. So here are some examples of exothermic and endothermic changes. All right. So in other words, we just found that delta H is the sign meaning change in enthalpy. Here are some examples of types of reaction. What I'm going to do now is I'm going to show you how we show the value. So this is methane burning. CH4 is methane. Methane is cooking gas. It's the big problem at the moment in quite a lot of the world because of Russia's behavior towards its what used to be a friend. The gas supplies have been cut off to a lot of the world. And a lot of the world is now, Western Europe used to get most of its gas from Russia, and now it's getting it from Africa and from Norway and other countries because we can't get it from Russia. So methane is used in Britain. At the moment, the temperature in the UK is very low. Over the last few days, it has been down to -10 in some places, and some days it has not got above 0. So we need to heat our houses, and many people use methane burning. Here it is, CH4 plus 2O2 goes to CO2 and 2 waters, and delta H is minus 890 kilojoules per mole. That kJ/mole is kilojoules per mole. When nitrogen and oxygen react together, they form nitrogen monoxide, 1 oxygen, NO. So N2 plus O2 goes to 2NO, and that takes in heat. That's plus 181. So I want you to understand this. In this top equation, this is minus because it is losing that energy it's given out, whereas in the bottom one, this is taken in. The bottom reaction happens during lightning storms in Kenya. You will smell, when there is a lightning storm, you will smell nitrogen and oxygen making nitrogen monoxide. Sometimes when there is lightning, you can smell, it smells a bit like metal. And that is because only in lightning is there enough energy to break up the nitrogen molecule, which is very strongly held together with a triple bond. So this is what I'm saying, is that negative there means it's exothermic, and the positive there means it's endothermic. So those are very important ideas. Okay. All right. So far we've done quite a lot. Exothermic is a reaction which gives out heat. Delta H is the sign for the change in the heat energy. In an exothermic reaction, heat is lost. It's given out by the wood in the stove. It is lost. So we say delta H is negative. In an endothermic reaction, heat is taken in from the surroundings, so the chemicals get colder. And you may perhaps, if you're a big sports player, you might have come across cold packs. Has anybody come across a cold pack in sports? When you have an injury, they will sometimes have a plastic container, and they break the inside and they put it on the injury, and it takes the heat away. They are very, very powerful, and they are endothermic reactions, and those endothermic reactions take the heat out of your injury. Okay, let's go on. So the next thing to talk about is the thing which I was showing on the board just now, where I wrote, and they're called energy profile diagrams. And this is what I just showed you. This is an exothermic one, and this is worth writing down if you are writing things down. Excuse me. The y-axis, the vertical axis, is energy, and along the bottom is progress or course of reaction, in other words, where we are. And we start with the reactants, and we go up and we go down to products. And that little hump that we have to go over when we have to light the wood, that is called activation energy. And that's an important idea, that many reactions need something to start them. They keep going when they're going. So you can have a fire which will go forever. In the Stone Age times, we believe that once people had fire, even if they went traveling, they would take some fire with them so they didn't have to start it again, because that was difficult. But they could keep the fire going for many years. That is because the heat given out can supply the energy of activation for some more wood. So I have my fire, it is burning down, I have some hot ash, I put on new wood, and this new wood needs energy of activation, but the hot ash provides that energy, gives it the energy so it can go up and then fall down the other side. So if you're writing that down, that's great. Energy of activation, here are the reactants, here are the products. That's that one. So that's exothermic. Endothermic looks like this. So we start with reactants, we end with products, but this time products are higher up than reactants. Now it's very important that you recognize these two graphs. The activation energy is still the distance from the reactants up to the top of the peak, but this time the peak doesn't go down as far as the reactants were. So if this is the energy up the side, we say the reactants are at 0 and the products will be at plus whatever, 200, 500, doesn't matter. And the energy difference, if you look at both of these graphs, is the difference between the reactants and the products. So in this one, energy is given out because the products are lower. And in this one, energy is taken in because they are higher. Okay, lower and higher. Okay, so I'm going to stop sharing there just for a minute. Okay, do you need more time to write that down, or are you okay? Does anybody need more time to write it down? Okay, I'll go back to the slide for a minute. I'll go back to the slide. So the exothermic one is behind me, but here is the endothermic one. Energy up the side, course or progress of reaction along the bottom. This is endothermic because the reactants are lower. It goes up, it comes down, but it does not come down as far as the beginning. Okay, so the energy absorbed or taken in is the blue line there, the blue arrow. That's the endothermic reaction. Remember, delta H will be positive. Delta H will be positive. Just 2 more minutes before I move on. Okay, so we're going to move on now, and I want to get you to have a little bit of an idea about this. In this diagram here, I'm going to go back one to the exothermic reaction. I want you to understand that we cannot measure the energy of this level or this level down here, the reactants or the products, only the difference. But the difference is always the same. It doesn't matter whether you measure it in London or Nairobi or Canberra or wherever. It doesn't matter. It's always the same. Okay, it's the same, exactly the same amount of energy. So from reactants to products does not change. In other words, the difference between reactants and products does not change. That's really quite important, because the next idea is something called Hess's law. And if you are one of those people writing things down, then it is important to write this down. Don't worry about the multi-step thing. Just write down the overall enthalpy change or heat energy change for a reaction depends only on the first and last, or initial and final states, and is independent of the route taken. In other words, it doesn't matter how I get there. It just matters where I start and where I end. Okay. That's really important as an idea, that where we start and where we end tells me what the overall energy change is going to be. And I'll give an example of this. I'll give you just a moment. So the overall energy change only depends on the initial and final states and does not depend on or is independent of the route taken. That's very important as an idea. If you think about the diagram that I drew behind me, it will be useful just to realize that the difference between the reactants and the products is always the same. So it doesn't matter where we go on the way. Sophia, if you're there, do we finish at 4:30? Sorry, 5:30.
Yes, we can go to 5:30.
Okay, cool, thanks.
Thank you.
Okay. Okay. Now I'm going to show you this, but I'm going to move on from it to something else, just so you can get an idea of what I'm talking about. So if I have the reactants, the chemicals which I am starting with, and the products, then it shouldn't matter whether I go one step or two different steps, because the level of reactants and products is the same. I'm going to stop sharing. I'm going to come back to my picture behind me, and I'm going to take an example. Okay. So you may have done some organic chemistry. If you have done organic chemistry, you will have perhaps come across ethene and ethanol. You may well not have come across ethanol yet. It's an alkanol. You may not have done it. But the point is that ethene can turn into ethanol quite easily. I'm now going to change this diagram so it shows me that, okay? But I'm going to show you it in a slightly odd way. So ethene is here, and ethanol is here. And both ethene and ethanol burn to form carbon dioxide and water. Now, because ethene burns to make carbon dioxide and water, and ethanol burns to make carbon dioxide and water, the carbon dioxide and water made by ethene or ethanol are the same. They're exactly the same. They make no difference at all. So carbon dioxide and water is a fixed level. Ethene is also a fixed level. It doesn't matter whether your ethene is in Nairobi or London or Cardiff, or it doesn't make any difference. It's the same chemical, so it's at a level. So if I know the numbers for taking ethene and burning it into carbon dioxide and water. And I know for taking ethanol and burning it and turning it into carbon dioxide and water. And I'm going to make up two numbers. These are not real numbers. I'm making them up, but it will explain something. Let us say that I get out 1,000 kilojoules burning a mole of ethene. Let us say I get out 2,000 kilojoules burning a mole of ethanol. Okay, it's higher up, gives out more energy. Now I can work out how much energy it will take me to turn ethene into ethanol. That's really powerful. This guy called Hess, he was a Russian a really long time ago, and he did many experiments, and he found this was true, that it doesn't matter where I start and where I finish, as long as these are constant, nobody cares the route. So because this is 1,000 from here to here, and this is 2,000 from here to here, then I know that to go from here up to ethanol must be 1,000. But this is minus 1,000 going down. This is minus negative 2,000 going down to here. Therefore, it would be, if I reverse it from here up to here, that would be a clever trick. If you as a chemist can make carbon dioxide and water into ethanol, then that's quite clever. Plants can do it, but we're not very good at it. So that would be plus 2,000. From here to there would be the reverse of this. If this is negative 2,000, that will be positive 2,000. So if I know the value for burning ethene and the value for burning ethanol, I can find the difference between them, and I can work out that if I want to make ethene into ethanol, it will cost me, I will have to add 1,000. If I make ethanol into ethene, I will get out 1,000. That is Hess's law. It depends only on where I start and where I finish. It doesn't matter whether I do it in one step or two steps, no difference at all. Sorry, I'll just get the camera a bit bigger. I mean, the picture a little bit bigger. So here's ethene. There's the carbon dioxide and water. Here's ethanol. 1,000 from here down to here. 2,000 from ethanol down. That means I know that the difference between ethene and ethanol is 1,000. That's really important that you get that as an idea, because it is fundamental in energy. Bye, Gotti. Okay, sharing my screen again. Oh, I've got to change my camera first. Okay, now I'm going to give you, so this is, I'm going to give you another way of thinking about this. Instead of it being reactants and products and intermediates, I'm going to talk about a journey. And the journey goes like this. I want to go from Nairobi to Malindi. If you don't know where Malindi is, you should. I'm going to catch the bus and I'm going to go from Nairobi to Mombasa. And that's a really long journey. And then I'm going to catch the bus from Mombasa to Malindi. I do not want to catch the bus from Nairobi straight to Malindi because the road is very small. The C103 is very small and it can be dangerous. So I have to go from Nairobi to Mombasa, Mombasa to Malindi. Okay, but I have to check my tickets. I have to make sure I have the right tickets. So what happens if I turn up with the wrong tickets? Because sometimes in a question, they have the reactants to the intermediates and the products to, look, I've changed the direction of the arrow, the products to the intermediates. It's like going from Nairobi to Malindi via Mombasa and going from Nairobi and getting on the bus and showing the ticket, and I get to Mombasa and I get on the bus and the man says no, because I have the ticket from Malindi back to Mombasa. I'm showing from Nairobi to Mombasa, the arrow was yes, that's my outward ticket. And then I get on the bus here and this arrow says that's like the return from Malindi. So what we've got to do sometimes is just turn it round. So I've got to make sure I've got the right ticket. It's in the right direction. That is very, very important. It's a silly example, but what I want you to understand is that from Nairobi to Malindi, I have to go from Nairobi to Mombasa, and then I can't use a ticket which is in the wrong direction. So I need to reverse this one. So let's just look at, I'm not going to do that one yet because it's a little bit hard. So I'm going to pick you a different example. And I'm going to ask you to see if you can have a go at it. You can just have a moment. We've got a little while left, just a few minutes left. So I want you to just see if you can get what to do. So I'm going to change the camera again. Whoops. Oh. So, yeah. This is very clever plastic. It's plastic which you can stick to a wall if you don't have a board. Oh no. Just a moment. Okay. If I burn methane, delta H is negative 900 kilojoules per mole. If I burn methanol to carbon dioxide and water, the difference is, whoops, oh, don't be silly. Oh no, I'll hold it to you here. So, this is falling to pieces on my own wall. So for burning methane, it's minus 900. For burning methanol, it is negative 1120. What I want to know is what is true, what is the value for turning methane into methanol. Okay, so here's the problem. The problem apart from my wall falling to pieces. If I burn methane, negative 900. If I burn methanol, which can be made from methane, it's negative 11 to 1120. What I want to know is how much energy do I have to put into methane to turn it into methanol? Have a look. I'm just going to get another piece of paper and stick it to the wall. Have a think. Talk to somebody else. So let's just change the camera again. I'll be very quick because it's nearly the end of the lesson. Okay. So I know that if I burn methane and I make it into carbon dioxide and water, it gives out 900. What I want to know is if I turn it into methanol, what is this energy here? If this is negative 1120. So this is like the Nairobi, Mombasa, and so on. In other words, this here is the same as that. Okay? So this arrow is in the right direction, but that one is in the wrong direction. So what will the total be across the top? Has anybody got an answer? Anybody got an answer? Hi guys, we've got about 2 minutes. Somebody come up with an answer. So there it is. Methane. So what I'm saying is that going down like that is okay, but this one we've been given in that direction. I want to go that way. So if I change the direction of the arrow, I change the sign. So negative becomes positive. Okay, so anybody got an answer? Anybody got an answer? Somebody be brave. No? Okay. Let's have a look at it. So, from methane.
We have an answer here.
Oh, we do?
Yes, there is one.
Good. So, Mercy reckons 2020. Is that what Mercy reckons?
Yes, yes.
2020? Not
Yeah,
quite. I like that you had a go, Mercy. Well done. I'm really impressed. I really am. Very, very good, but it's not right. I'll show you why. So from here to here is the same as going down here and up there. So this arrow is okay, but this one is in the wrong direction. So what I need to do is to change this arrow up. So that is the same as this. Look, Nairobi, Mombasa, Malindi. I need to go Nairobi, Mombasa, Malindi, because I want to go Nairobi, Malindi. So I need to go up here. So if I change this arrow up, then I change this here from negative to positive. And then it is negative 900 and positive 1120, which makes positive 220. 220. If anybody there was thinking that it might be 220, well done. But I would like you to have a go. I'm really impressed with Mercy because they had a go and that was important. Okay. I'm sorry I was late today. I had problems with my Wi-Fi, and as you see, I have problems with my stick-on board. I will make that better for next time. We will continue with this next time. I hope that some of that went in. Remember, exothermic gives out heat. Delta H, the heat is lost. So we write the equation and it is minus the number at the end. Endothermic takes in heat. Heat has to be added. So it's plus and the number at the end. The change is delta H. It's measured in kilojoules per mole. And this is called Hess's law. Hess's law says if we know 2 of the changes out of 3, we can find the 3rd change. We'll carry on next week. But until then, I say, Asante sana.
Asante, Teacher Mark.
Thank you very much. Thank you very much, Wamuini, Ushirika, Silver Spring, Genesis, Mathari, Mix Select, very good. Well done. Oh, what was Horizon? Great. Great to see you guys. Thank you very much indeed. And
Thank you.
I'll say bye-bye.
Thank you very
Bye now.
much. Bye.
Thank you.